We started with a steel bucket which we filled with a plaster and sand mixture. We then pushed a smaller bucket into the wet plaster to create a cavity for our combustion chamber. Next, we drilled a hole into the side of the bucket for our forced air input. When the foundry was ready, we surrounded the crucible with briquettes and lit them. Finally, when the foundry reached an adequate temperature, we could begin melting cans. To make our crucible, we took an old fire extinguisher and cut it in half. Once the aluminum was fully melted, it developed a layer of slag on top. When pouring, the slag stuck to the sides of the crucible, allowing pure aluminum to flow out from underneath.
Here you can see us putting additional briquettes into the foundry in order to bring the temperature up to the melting point of aluminum. For our forced air input, we chose to use a hair dryer secured to a PVC pipe, which was then coupled with a steel pipe that fit securely into the hole in the side of the foundry.
Once the foundry reaches a high enough temperature, we can begin melting cans. As the pool of molten aluminum rises, it becomes easier and faster to melt cans due to a greater surface area of heat in contact with the can. We used a push rod in order to submerge the can as much as possible. Typically, each pour consists of about 40 to 50 cans. Tapping the push rod on the side of the crucible and foundry is to help prevent slag buildup on the end of the push rod. We periodically stirred the pool of aluminum to ensure that the surface exposed to air did not partially solidify.
When manufacturing the ingots, it is crucial that there is enough molten aluminum in the crucible for casting. When a sufficient amount of aluminum was in the crucible, we carefully removed it, repositioned the tongs, and began pouring into our muffin tin. After pouring, we either left it to cool from ambient air or dumped water on it to achieve a faster cooling. After each pour, we set aside the active coals for continued use and removed the ash from the combustion chamber. We did this to avoid the formation of an insulating layer in the bottom, which would have led to an insufficient amount of heat from underneath the crucible.
After multiple uses of the foundry, fatigue and cracking appeared on our foundry elements. The multiple pours that we did allowed us to improve on our processing technique. This, however, created an issue that the temperature of the molten aluminum exceeded the melting point of the muffin tin, which caused a breach in the mold. We then used a steel paint can that was able to handle the energy for our later ingots.
After casting the aluminum, a sample was chosen to be fast cooled and another to be slow cooled. Immediately, the appearance of the surfaces were different from one another. From here, we tested the properties using the Rockwell hardness test. This test gave us a hardness value which is correlated to the material's resistance to plastic deformation. The instrument used for this test was calibrated with known metal samples to give an accurate reading. A total of 12 trials were performed on each sample, starting from the edge and moving towards the center of each cross-section. The test showed a change in properties throughout the ingot.
The slow-cooled ingot had a higher average hardness rating than the fast-cooled ingot. The fast-cooled ingot developed a consistent trend as we moved closer to the center, which can be attributed to a more consistent grain size. Though we saw these trends in the slow and fast-cooled samples, there were a lot of outliers and a high standard deviation. On the other hand, the alloy had a very clear and consistent hardness trend, which is most likely due to the higher quality metal used. What this information conveyed to us is that manufacturing quality metal is a much more complex process than melting cans in a chopped-up fire extinguisher. One method that we could implement to see more consistent properties would be to control our cooling more accurately using calculated rates with known temperatures.